All right, so we were working on these examples on partial fractions, correct? Where did we leave off? We finished C? We got the A, B, and C? Should I finish it? No? Yes? Okay, then you need to help me because I don't have any of that written down. Our new integrals should have been, okay, go ahead.
It's going to be x over x plus 1, x minus 1 squared.
What is it?
Oh, no, never mind. That's a over x plus 1.
Let me see. Take a look at this. This what you got? Let me borrow it for a second. Okay, so we had A, which was negative 1/4 over x plus 1. Then plus B, which we got to be 1/4 over x minus 1. And then C, which we got to be 1/2 over x minus 1 squared dx. Does everyone agree with that?
Yeah.
Now, and this was just, here you go. This was just one part of it, right? Wasn't there another part? Because we had done long division. And when we did the long division, in your notes, we had an x plus 1 and then plus the remainder out here, right? So we integrated x plus 1 and we got, did we? 1/2 x squared plus x? Plus
4 when you.
The 4 is multiplied by the integral.
Oh, you need a 4 down here?
The 4 is the integral.
Right here?
Yes.
Okay. All right, so I left off with us just needing to resolve this. All right, so there's a 4 out here. Each one of these I should be able to handle. So this first one, because it's a linear expression, you have a constant up top. This should be a natural log. This one, same thing. Linear expression, constant on top. That's going to be a natural log. This one is not going to be a natural log because it's a linear expression squared. Right? So, but we could still do that because that was in our list of preliminary integrals. So let's handle those first two. I bring the negative 1/4 out. It multiplies times 4 and becomes negative 1. So we'll have negative natural log of x plus 1. And then this one, positive 1/4 comes out, hits the 4, so that's positive 1, natural log of x minus 1. And then who can tell me how I'm going to do this one? Just a u sub. What's u going to be? X minus 1. And so this really will turn into, like bring the 1/2 out, it's really like 1 over u squared. And the antiderivative of 1 over u squared is negative 1 over u. I'm hoping we've done that enough that if you had to do that, you could. Yes? No? Yes. So I'll have a plus and then 1/2, and then we're saying negative 1 over u, right? Which should be x plus 1, or x minus 1. And, uh-oh, I forgot my 4.
No, it went away when you pulled out the 1.
Yeah, I need this 4 for this half. So that would actually be a what? 2. And then plus c. And then that should be it. Now, what was the part, again, that we integrated in the very beginning? Was it this right here?
Yes.
So 1/2 x squared plus x. So your final answer, okay, after all the work we did, should be 1/2 x squared plus x minus natural log of x plus 1 plus natural log of x minus 1 plus, well, I'll make this a minus, minus 2 over x minus 1 plus c. All right. Ron, you're going to have to pull up somewhere. I don't know if there's enough room. I don't care. Yeah, that's fine. Still knocked my camera over. Oh, is that you?
Yeah.
You got it?
Yeah.
No, go ahead. I don't want to knock over anything over here. You good? Yeah. Apparently. Got rejected. Okay. Let's move on, though. We're going to do the next integral up here. I did finish all the problems, the homework problems for this section, the videos for them. So all the problems that I'm going to ask you to do for homework for this section, the solutions are up on YouTube now. All right. All right. So for D, we have integral 2x squared minus 4x, or sorry, minus x plus 4 over x cubed plus 4x dx. So we have a quadratic function on top, a quadratic polynomial. We have a cubic polynomial on the bottom, right? So this is a rational function. So we're starting to think partial fractions possibly. The degree of the numerator is 2. The degree of the denominator is 3. So are we going to need long division? No long division, right? This power, if it's bigger than this, we're free to move on to the next step. So what was the next step? Remember? Factor the bottom, right? Factor the bottom if possible. Does that factor? It does, but not very much, right? All you can do is what? Just pull an x out. So this becomes integral 2x squared minus x plus 4 over x times x squared plus 4 dx. Now, if you look back if you have your notes with you, I want you to kind of look back at A, B, and C. For part A, we had long division, and it worked out. We didn't even need to do any of the partial fraction stuff. It was just long division. Part B, we did a factoring out, right? And then we factored the entire denominator. Can somebody tell me for part B, when we factored the denominator, what we had down there? It was like x and then, what is it? 2x minus 1 and x plus 2. And then we had all the junk on top, right? That was part B. And so we said for part B that this was what? 1, 2, 3 distinct linear factors, right? And so then that force us to do a over x, b over 2x minus 1, and then c over this, right? In part C, our denominator, once we went through and cleaned it up, it factored to be, was it x plus 1 times x minus 1 squared when we factored? And so we said that this was, again, 2 distinct linear factors, but one of them was repeated. And so we still dealt with that by doing a over this, b over this, but without the squared, and then c over this with the squared. You all kind of remember doing that? Okay, this right here is different than those in the sense that we have a distinct linear factor here. We do have a distinct linear factor. It's really like that, right? Or if you like, you could write x minus 0. That's a distinct linear factor. This, though, is not a distinct linear factor. It's a quadratic factor, right? And it's irreducible, meaning that you can't factor x squared plus 4 any further, can you? Can't be broken down? If it was x squared minus 4, yes, it could be broken down. So the question becomes, how do we handle something with partial fractions if you have an irreducible quadratic factor? So here's what you do. That's what you do. Completing the square was suggested. That is what you do if that's the only thing down there. But that's not the only thing down here. We have an x attached to it. We will eventually probably need that, though. Because remember I said we're going to build a problem to the point where we can do something from the preliminary stuff? All right, so here's what we'll do. The partial fraction technique for this one is to rewrite everything. every single time you ever see a linear factor, distinct linear factor, you put A over that distinct linear factor. So that's not different, right? That's the same as what we've done before, right? Yeah? Yeah. Okay. Plus, now you may be thinking, well, why not just put B over this, right? Put B over this.
Is it going to be like bx plus c?
That's the difference. Anytime you have an irreducible quadratic like this, you don't put B over it, you put bx plus c over the distinct linear, the irreducible quadratic. So think about why we would do this. The reason we did this is because the bottom is linear, the top is a constant, right? What's the derivative of a linear function? A constant, right? So we know that if this somehow becomes a u, the derivative of it is up there, and we can handle it with natural log. This, though, if the bottom is an irreducible quadratic, what is the derivative of an irreducible quadratic? It's linear, right? So we want the top to be linear so we can call the bottom u and then do the same sort of thing. Does that make sense? Now, the notes explain this, and I haven't even referred to these, have I? I haven't even, because I told you I think they're too crazy to look at right away. I will come back to this and I'll recap it. But first, let's just see the rules in action. So for every irreducible quadratic factor, I will place it underneath some arbitrary linear expression. Okay? And that's it. Now we come through and do what we did before. Multiply both sides by the LCD. So my think tank's going to start out today. Whoever wants to at the table. If you multiply both sides by the LCD, what's the left side going to be if I multiply by the LCD? Hold on. What?
Squared minus x plus 1.
All right, 2x squared, Christy's out. 2x squared minus x plus 4. Same table. What's this going to be? A
ax squared plus 4.
parentheses?
Yes.
Okay. Because the x's cancel. And then here, what cancels? So, anyone?
bx plus c times x.
So plus bx plus c, right? Put that in parentheses. That's very important. You put that in parentheses because it's that times whatever was left over here. What's still left over? The x. Does everybody see that? That's what happens when you multiply both sides by the LCD. The things that cancel. And imagine this thing right here. The x's go away. Imagine this thing right here. The x squared plus 4's go away. Do y'all see it? All right. Now, last class we played this game where remember I was talking about the little God complex, right? And you get let something be whatever you want it to be, and then you get things to go away, right? When you look at this here, we're trying to solve for how many different variables? 3 variables, right? So let's see. Can I get A? Well, I'd have to kill this off over here, right? What could I do to kill everything off over here? Let x be 0. And right, if x was 0, it would kill off everything, and I could just get this. Are you ever going to be able to kill off A? Why not?
Because the square will turn negatives into positives.
That's right. You can never plug a number in here that's going to make this 0. Unless you bring in the imaginary numbers, and we're not going to do that, right? So you can't kill this off, which means there's no way you can actually get rid of the A ever. So we need to go to the longer technique. Did I do the longer technique last time? I didn't, right? So what is the longer technique? The longer technique is you just have to multiply everything out on this side. You actually have to distribute the A through. Here you have to distribute the X through. You might remember this from pre-cal.
Then you have to put all the x squares together. The x
Then you collect like terms, yep. So let me put this together. So I would get ax squared plus 4a plus bx squared plus cx. So that's just distributing through. When you get things like this, 4 times a, we usually write the 4 times a. We don't write a times 4, right? Same thing with this. Cx, we usually put the c in front of the x because c is going to be a number at some point, right? So now what we do is we rewrite the right side and we collect like terms. So I'm going to go slow this first time through. Those are my x squared terms, right? So I'm just going to place them side by side. Ax squared plus bx squared. So I've taken care of those two. I'm just kind of I'm rewriting things. Now I'd like for you to find anything in here that has just x in it. Just the cx right here. So I've taken care of that. And now write down anything that doesn't have any x's in it. 4a. You with me? All right, now if you have like terms, like these two, that means there's something I can factor out of both. What can I factor out of both of these? An x squared, right? So you would normally write it like this, right? You would write x squared a plus b. Like if you pull the x squared out, that's the way you'd write it. But is it incorrect to write it this way? Oh. With the x squared in the back. No, because it's the same thing, right? It's going to multiply through. You get the same exact expression. So I'm going to do it that way, and you'll see why. A plus b x squared, then plus cx plus 4a. So I didn't have any more x's to group together here and anything else without x's, so that's the way it's written. All right? So in the long way, you're not trying to kill anything off. You're just trying to multiply it all out, get all like terms together, group them all up, and then take a look at them. If this equation is going to be true, then do you agree that the number in front of x squared here must be equal to the number in front of x squared here? However many x squareds there are over there must match how many x squareds there are over here. Yes? And the number in front of x here, which is what? Negative 1. That number of x's needs to match up with the number in front of x here, right? We're trying to say these two sides are equal to each other. So what we're doing is we're matching coefficients. The coefficient of x squared must match the coefficient of x squared. The coefficient of x must match this coefficient of x. And the number that's by itself, 4, must match the thing out here that's by itself without any x's. Right? So what we get from this are three relationships, right? We get the relationship between a plus b and 2, the relationship between c and negative 1, and the relationship between 4a and 4. And that's three equations that we can now create. And there are three unknowns, aren't there? And so I'm going to write down those three equations using the symbol for a system of equations. The first equation says a plus b must equal what? 2. So I'm going to write a plus b must equal 2. And now I left a space here because in reality my three equations, there's three variables, a, b, and c. So I'm leaving a column for each variable. What does my next equation say? C must be negative 1. Well, that's nice. C is negative 1. And then what does the last equation say? 4a must equal 4. What's that?
A equals 1, B equals 1, C equals negative 1.
Yeah, so from this we should be able to get this. I mean, this is not going to require much work, right? Because I already know what C is. C must be negative 1. Do I know what A is? Solve this equation, so I know what A is. And if I know what A is, can I get B? Yes. But the bigger picture is that with this process, you actually create a system of equations. And this system of equations could be very easy to solve, like this one, or it could be very difficult to solve. Just depends on the problem. So we'll look at one that's a little more difficult than this in a minute, but everyone with me? So A is 1. C is negative 1, and what's B? How do we get it? Well, A is 1, right? So just move 1 to the other side and subtract 1 on both sides. So B is 1. That's what we needed. We needed A, B, and C. So we have integral. It was A over, sorry, I shouldn't write A. It was A over X, right? A over X. So A for us was 1, so 1 over X. Then it was plus, oh wait, didn't we do long division? No, we didn't, not on this one, never mind. Then it was bx plus c over x squared plus 4. Bx plus c, so b was 1. So 1x plus c, but what's c? Negative 1, so x minus 1, is that all right? Over x squared plus 4 dx. I think we all would agree that that first one is easy, right? Natural log of x. How about this one? A u sub? You'll be off a little bit, won't you? There's a couple of ways you can solve this, so I'm gonna take some volunteer answers here on how you would want to solve this.
First, split them up
You want to split them up?
into 2 different intervals.
Okay, that is definitely one approach. Another approach would be try u sub and see what happens. Just like let u be the whole bottom. And the derivative of that is what? 2x, and you're off, but you could tweak it maybe. But I like the idea of splitting because the splitting should come out pretty clean. Natural log absolute value of x. That's the antiderivative of this. Plus 2 new integrals, x over x squared plus 4 dx, and then minus integral 1 over x squared plus 4 dx. So putting the x over this, the negative 1 over this, and I pulled the negative out. Everybody follow that? All right, let's move to the next table. So any ideas on either one of these integrals? U sub on which one? First one, U sub, yep, that's going to work. How about this one? Let them think about it. While they're thinking about it, I'm going to do some U sub over here. If you do a u sub on this one, right? U is the entire denominator. So u is x squared plus 4. The derivative of that is 2x dx. Do you have 2x dx? No, you're off, so you scale by 1/2. And so that one works this way. And then, yes, arctan. All right, this is the one that we love to see. 1 over variable squared plus constant squared. So this one's arctan. So minus, how does that formula work again? It's minus formula 17. 1 over a, what's a for us here? 2, it's the square root of this. So 1 over 2, arctangent of what? U over a, so for us, x over 2 plus some constant. Yes?
For that arctan one, could you factor out the x with the squared and then put it in the parentheses?
Not sure.
X plus 2 squared on
X plus 2 squared, though, is not x squared plus 4. So we good? Sure there's no questions? Kiki, when you said split them apart, did you see that you would be able to do both of those things ahead of time?
Oh,
kind of? Yes? Did you see arctan there?
No.
No? Okay. Just curious, that's all. All right, let's look at was this the last example? 4x squared minus 3x squared, or minus 3x plus 2 over 4x squared minus 4x plus 3. All right, we're back at, going back to the table there in the back corner, Vanessa, Rubin. Anyone? Okay, which means long division first. All right, so we've got to do that. So here comes long division. 4x squared minus 3x plus 2. So I did long division in my college algebra class yesterday. They didn't like it. They didn't like it. And I told them that in my Cal 2 class, we're actually using it. And they didn't care. 14. They said they would deal with that when they get here. But for now, they didn't like it. All right, so what is the first number that I'm going to multiply by? 1, right? 1 is going to create what I need here, 4x squared minus 4x plus 3. I come through, I subtract the row. So minus, plus, minus, right? So it became minus, plus, minus. So what's remaining down here? X minus 1? Can I keep going? No. Long division is over. So I put plus the remainder over the divisor. And that's going to be my new integrand, that right there. One piece of it I'll be able to integrate pretty easily, right? The other, I'm going to have to take a look at. So my new integral is 1 plus x minus 1 over 4x squared minus x plus 3 dx. Which is x plus the integral of x minus 1 times 4x squared minus x plus 3 dx.
Minus 4.
Yeah, did I forget to write it over there too?
Yeah.
Oh, forgot to write it in 2 places. What was I looking at? Okay? Good up to here? What now? We're at Ethan's table. Anyone over there?
Split it up.
How do you mean?
Can you factor out the bottom?
Okay, so yes, you always look, can we factor the bottom? If we can, then we'll probably get distinct linear factors and we'll use the A and the B thing. If this factors. So does it factor?
It's the same as the original, so what would
What's that?
it's the same as the original.
We never tried factoring here, right? We never did because it was the same degree, so we just divided long division first. This is our first real attempt to factor it. Does it factor? It does? I'll put it up here. Okay, we are at x plus integral. The top is x minus 1, and the bottom factors to b. Should we just do, like, take out a sheet of paper? Let's take a quiz. Everyone factor this? Come on, y'all got to be able to factor this. It doesn't factor?
looks like it does, but there's a negative. There's a negative messing it up.
So it doesn't factor? It does? It doesn't? Uh-oh. All right, so I'm only going to show this one time because we shouldn't be even taking time on this. But
No, it should work.
so you multiply those two numbers together, right? You get 12. You look at the number in the middle, which is -4. You have to come up with two numbers that multiply to be this, but simultaneously those two numbers must add to be this. So the only two numbers that you're going to get to multiply to be 12 would be 1 and 12, 2 and 6, 3 and 4. And of course, you could also do -1, -12, -2, -6, -3, -4, right? But there's no other way to get 12 than these combinations, right? But if you add any of these two together, you cannot get -4, right? None of these add up to be -4. So, does not factor.
Can we use the formula?
What formula?
The negative b plus and
Like the quadratic formula? That would give us a solution, but see, we don't have an equation, right? First of all, we don't have an equation. The reason I'm not saying no is because you can actually use a quadratic formula to factor something, but it's a little tricky. What's probably going to happen is you're going to get either imaginary numbers or you're going to get irrational numbers. Just think about the part in the quadratic formula that would be this piece right here.
It's
Well,
going to be negative.
It would be negative, would it? It would be b, this is b, right? B squared would be 16, minus 4 times a would be 4, and then c would be 3. And so you get 16 minus, it would be a negative number, which means it's an irrational number, which means this does not factor. Okay, just because this fails doesn't mean it doesn't factor, it just means you can't factor it, right? There's a difference, right? It just doesn't factor over numbers that we know out of our heads. This proves it can't factor over the real numbers, period. So we are stuck now with a linear expression over an irreducible quadratic, right? And we're moving on. Paul, Luke, Matthew, how do you deal with a linear expression over an irreducible quadratic? How did I show you? You should try and deal with a linear expression over an irreducible quadratic. Take your time. Take your time. I'm hearing complete the square.
At the bottom?
I agree, complete the square will come into play. Not yet, though.
After you pull out the
Nope. Anyone? Basic U-Substitution first. Look at this. This is really important because I do this different than the book does this. All right? This is the technique I always use when I see an irreducible quadratic and a linear expression on top. I always try and make the numerator look like the derivative of the denominator. That's what I always like to do. So I let the bottom be u. I let the denominator, the derivative, let's see. What would the derivative here be? 8x minus 4, right? Parentheses dx. I did this last class. Let's see if this is starting to set in a little bit. I would love my numerator to be 8x minus 4. It's not even close to being 8x minus 4, right? So what did I do to force it to be 8x minus 4? What did I do first?
8 over 8.
First, I'm going to do 8 over 8 out here. Multiply by 8 over 8 right out here. Then pass the 8 on the top through both terms on the numerator. What do I still have outside the integral? 1 over 8. I passed the 8 through to both terms. Don't forget to pass that 8 through here. I did number 31 this morning. It was the first problem I did this morning. Guess I was getting warmed up because I forgot to pass this number through both. And I did the problem took me like 20 minutes, and then I realized I messed up, and then I had to redo the entire problem. So it's not on the video. You won't see it. Yeah, it's deleted already. But I'm just pointing out, don't forget to pass that 8 or whatever the number is through to both terms. And then on the bottom, you still have this, right? So does this match yet? Does not match. What I really want to have here is what? Minus 4. Secret 0. We have a hidden 0 here. So this is where we come in here and we say right next to this x, right behind it is, what do I want? Minus 4, but I can't just minus 4. I also have to what? Add 4. Now look, I've had students say this to me before, and this is correct. Look, if you have 8x minus 8, some people will just look at that and say, obviously that's 8x minus 4 minus 4. Right? I mean, isn't it? Isn't 8x minus 8 8x minus 4 minus 4? And I'm not here to disagree with you. But potentially, these could be numbers that are not clean. They could be fractions. And so this hidden 0 is just something that I show you because it will always work that way. You could just, subtract it and add it and then deal with this other thing in a minute. Do you understand what I'm saying?
Cheating.
What is this one? This way?
It's cheating.
That's cheating? It's 0.
You can't add a 0.
Sure you can.
How do you add nothing?
You add nothing and it doesn't change, right?
Yeah, but you can't add anything.
Yeah, but look, in reality, if I wanted to do that, look, I have 0. and
You
I
stay
add
out of this.
It's nothing. Look at that. I can also try and
It's
divide.
actually,
He's the
We're-
teacher. It's like 30 of us versus 1 of him.
do you remember, were you in the after class, were you down there when we were talking about the 12 field axioms? Like what it requires for a number system to be considered a field?
Oh, we're talking about the dude starting at, what was it?
Like the different properties.
Terrence Howard's
Yeah.
on number
The real numbers,
1 times 1 is
You're,
2.
hey, you got.
yes, we were talking about that.
1 times 1 is 2.
Yes, that thing. So the real numbers make up what's called a field in mathematics. That's a very, very strong thing to be a field. And one of the properties of a field is that every field must have what's called an additive identity. It's a number within the numbers. There is some element that when you add it to every other number, it doesn't change the number. So x plus 0 equals 0. That is, 0 is the additive identity for the real number system. Similarly, every field must have what's called a multiplicative identity, a number that when you multiply it times any number in the field, you get itself. And 1 is the multiplicative identity. So as trivial as it may seem that, really we're kind of cheating, no, the real number system being a field guarantees us we can always add nothing to something, and it doesn't change the problem. So it's even more fundamental, I guess. All right, let's get back to the adding of the nothing. All right, so we go 8x, and then we go what? Minus 4 plus 4. There's my hidden 0. Then minus 8. All over 4x squared minus 4x plus 3 dx. All right. So where were we? We were at Luke, Paul. So we're up here at Zach, Chris, Ivana, Alejandro. Why am I doing this? Like, why am I trying to do all this voodoo magic stuff? Hold on.
So that our U-sub will work?
Okay, so that the U-sub that we originally wanted would work. So that means I'm going to split this, right, Ivana?
Yeah.
And you're telling me, Ivana, that then that first part where I split it, these two over this are going to work out, yes? Can you tell me, Ivana, what remains and how I will deal with that?
There'll be a -4 over top of that whole thing.
Mm-hmm.
And then the 4 can come out and it'll become a 2.
Okay,
And then the bottom, we have to complete the square.
there you go. That's it. So the whole idea behind this is that you almost had something in its derivative. You tweak it with this little magic thing that's happening, whatever, it's not magic. And then the first part becomes that nice thing you wanted. And what remains, notice what remains doesn't have an x anymore. See, the x threw everything off here, right? If that x wasn't there, we would have just completed the square and been done. But because the x is there, we couldn't. So we forced the x to be part of a nice thing, and then what remained is the number over the quadratic, and we'll complete it, complete the square. All right. So let's rewrite where we are here. We've got x plus 1/8 integral 8x minus 4 over 4x squared minus 4x plus 3 dx. That's one integral. The other integral is this minus this. That's -4. What happens when I bring -4 outside? -1/2. Okay. Integral, and then what? I pulled the -4 out already, so what's up there still? 1 over, and then the denominator, right? 4x squared minus 4x plus 3 dx.
Wouldn't it just be the substitute?
This one's going to be a basic U substitution. This one, because look, there's U. Where's its derivative? Right up there. That's exactly the derivative, perfect. It's almost like someone made it for us, right? Oh, wait, that was us. We made it like that, right? Like we did that so that that would work out, right? And then this one no longer has x up here. So how do we handle an irreducible quadratic with a constant on top? We complete the square. So you see, these are going back now. See, before we started, I said, what do we need to know how to do? And this right here, linear over irreducible quadratic, was one of the ones that we need to be able to do. Constant over irreducible quadratic, this one is something we need to be able to do. All right, completing of the square. Kiki said she's going to help me with this one because she said that she enjoyed completing of the square. Okay, well, we're back at this table, so someone up, and Christy's out. So when you come back through, if you already answered, you can't answer. That's correct. Do you want to go ahead and continue then? Alex? Yes? You have to make sure it's a 1 in front. So how do I do that? Just take a 4 out. So that gives me x squared minus x plus 3/4. I'm completing the square here, everyone, right? Then you identify the number in front of x, which for us is -1, right? And you take half of it. So I'll do that right here. -1, half of it. That's my first number that's going to come into play. Then I square that, don't I? -1/2 times -1/2 is going to be 1/4. And that's my second special number. Which one of these numbers is the one that I come in here with that 0 again? Which one of these do I use? The second one, right? The 1/4. And I'm going to do what with it in here? Plus it and minus it, right? Add it and subtract it. And where do I do that?
In between.
Right
Constant and the x.
between the x term and the constant. So I have 4x squared minus x plus 1/4 minus 1/4 plus 3/4. And I'm guaranteed, we're moving on to the next table. I'm guaranteed, who answered last time? Karen? Who did it? All of you did? It was like in unison? You're all, okay, so anyone, I don't care then, at that table. What are you guaranteed is going to happen here? Like with this. Perfect square trinomial right here, right? This is going to be x minus 1/2. Where'd that 1/2 come from? That's this number, right? Squared. And then this, you just put these together. What's -1/4 plus that? It's 1/2, right? That's all in parentheses with the 4 out front. So this expression becomes this expression, becomes this expression, becomes this expression. And so I can rewrite this integral right here. Oh, by the way, what was the antiderivative of this? Because of the way we designed it. This is 1 over u, right? So ln. So we should have 1/8 natural log of the whole u, right? 4x squared minus 4x plus 3. Okay, so that integral is taken care of. This one, we had a negative 1/2 out here, right? And we're going to put on the bottom here this expression. What about that 4? Pop it out, and this becomes really what? Negative 1/8? Integral of what? 1 over x minus 1/2 squared plus 1/2 dx. All right, we're moving back. Next table. Ruben, did you answer last, Ruben? Who answered over there? No? You answered, didn't you? I thought you and Kelly answered. No?
I kind of like,
You kind of, I heard you say long division, right?
yeah.
Okay. Ruben or Vanessa? This is formula 17, isn't it? This is formula 17. Now there's a little bit of an issue here because this is not just u, right? It's a little linear expression, so you might need, I don't know, this depends on you. Like if I was doing the problem, of course, I would just go right to the answer, but you might need to do a little quick u sub on this. Right, x is, u is this piece right here. The derivative of it is dx. And then that whole little, this whole little integral right here becomes integral 1 over u squared plus 1/2, right? That's all it is. And now you can go to formula 17. And what is a for us? Square root of 1/2. Square root of 1/2, right? It's always going to be the square root of this number. What is the square root of 1/2? That's 1 over root 2, which is fine with me if you write 1 over root 2. You could also write that as root 2 over 2. I don't care. I think I'm ready for the final answer, aren't you? All right, so we've got x plus 1/8 natural log 4x squared minus 4x plus 3. All right. Minus 1/8, right? Minus 1/8 times, now formula 17 is 1 over a arctangent u over a. What's 1 over a for us here in this problem? It's 1 over root 2, right? Which flips it and just makes it root 2. Arctangent of u over a, but what was u? X minus 1/2 over a, but a is 1 over root 2 or root 2 over 2, however you want to write it, plus c. And that's good enough. Yeah, you could do root 2 over 2 and then pop that 2 up top and make it a 2x minus 1. But you'd still have a root 2 on the bottom. So what do y'all think? Any, what's that? You want to check it? Really wouldn't be that bad. But, okay. So that's it, huh? Partial fractions? So I suggest you go and take a look at the, do all the homework. Some of the problems in the homework get a little more complicated than the ones that you see here. That's why I posted the solutions, so you could go take a look at them. And what did I give you last time for homework? Did I write down an assignment? Okay. 7 through 12 all? Okay, so what I'd like for you to do now is just do 13 through 41 odd. Hey, I did 13 through 41 odd. It was fun. It wasn't as long as the previous section's homework. But, yeah, I guess so. So everyone have that? Same page. So it's page 334. What I'm really looking for you to do is 7 through 41 odd. I think that's what I did on my videos. I asked you to do 7 through 12 last class because I was just trying to get you to, the first few problems all had the same technique. So I was just trying to give you a little repetition. Now, I have not done the evens. I didn't do the evens on the video, which makes me feel like the evens would be probably a good place to draw a test problem from, right? I haven't provided you the answer for it. All right. Now, 6.4 is the next section. We're not going to do 6.4. 6.4 is a section about using the actual table of integrals in the back of your book, but like the entire table, everything, all 100 and whatever, 120 formulas. So they give you in 6.4 some integrals where they just look really bad, and then you make like a basic U sub, and you look at it and you go, okay, yeah, that's formula 103, you know, and it's just an exercise in matching a pattern to a formula in the back. And I think it's, you know, there was a point in time in history where that was probably worth it to have that table and go to it, and that way you don't have to do the integral by hand. But nowadays, why go to the table when you can go to Wolfram Alpha and get that to do the entire integral for you anyway, right? So if we're going to be resourceful, going to a table is not option one, right? Resourcefulness means going to Wolfram Alpha and getting an answer. So, yes?
I was going to say, can we use the Wolfram Alpha on the test?
You know what? Let's raise your hand. Engineers first? Okay, I've got a stack of degrees. Just come up here. I'm going to give you your degree. Just write your name on it. Come on. Good try. All right, so 6.4 I'm skipping. All right. And that brings us to 6.6, which is called improper integrals. We can't do improper integrals yet because we've avoided something this entire time. And that was those numbers. Do you remember every homework problem, every homework set that I ever said, if there were numbers there, that you just ignore the numbers and don't worry about them, and we'll deal with them later, right? Well, now is later.
Wait, are we doing this now?
Yes, we're doing this now. Is that okay?
No, I remember.
Okay, all right. Just want to make sure it's okay with you before I proceed. All right, so we have to take a huge step back now, all right? Huge step back and take a look at some stuff that may seem completely unrelated to what we're doing, like what we've been doing. But I told you it was going to be that way. I told you that we're going to try and attack these problems, but the first thing we need to do is learn how to integrate. Once we learn how to integrate, then we can do some applications. So with that said, I'm going to, where is it? I had it open a little while ago.
You said it was 6.5?
No, I'm not doing 6.4 right now.
6.5.
This is actually 5.2, 5.3, and 5.5 all together in just one big blah. Okay, because we're going back, it's kind of hard to blah, yes. All right, can we, Vanessa, can you kill one light, please, for me? So like I said, kind of clear your head a little bit, and sorry to make some of you look backwards, but this is not really a chapter in the book, which is why I'm calling it Chapter R. And it's going to stand for Riemann Sums. Riemann Sums. So is everyone's mind cleared?
Is that a rapper?
Yes. Our motivation. So where are we going to start here with this brand new topic? The motivating idea is the classic area problem. So for many, many years, hundreds of years ago, depending on your view of the way things were or how they have come to be, I hope that we could all agree that at some point we started to separate ourselves with barriers, right? This is mine, this is yours, right? Stay off of my stuff, I'll stay out of your stuff, right? And we started to create these borders between us, right? Whether it be a group of people or countries or whatever, or this is my land, that's your land. And so at some point we had to figure out clever ways of measuring, how much that is. Like, what is that? How much is in there? So on a two-dimensional picture, this would be a representation of area, right? Length times width. And so we all know that the area of a rectangle is length times width, right? And if we got something more complicated like a triangle or something like that, and we wanted to know the area, then we know that that's what? What's the area of a triangle? 1/2 base times height, right? Yes. So why is it that way? Well, here's a different looking triangle that doesn't look like half of a square to me. Would you agree? If you turn it, I'm turning it.
Cut it, flip it, and paste it.
Yeah, so to do this, you actually have to create a second version of this, right? So draw another one of these, but take this and rotate it and flip it over and draw it backwards. It'll look like this. Ah, I messed it up. Okay. Good enough? Is that good enough? That's this picture like this. That's terrible. Yeah, I went too far out here. Yeah, it's not drawn to scale. Okay, is that a little better? All right, so now the height is this, and the base is now here, right? Do y'all see it? And then if you take some scissors and you just come and cut this off and take that and put it right here, then now you've created a rectangle. And how long is the rectangle here? The base, and how tall is it? The height. So the area of this whole thing should be base times height, right? But remember, I came in and created a duplicate copy. So this is twice as much as it should be. So that's why it's 1/2 base times height. Okay, so what I'm getting at is that as the geometric shapes became more complicated, we just got fancier and fancier with how we came up with ways to measure them until we got to something like that. And when we got to a circle, there's no way we could figure out how to come up with an easy way of determining the area. And so y'all are all, yeah, those idiots, pi r squared, right? Like, it's just pi r squared. You got a circle, it's so simple. These people were idiots. So, but the thing is, they didn't know that, right? They didn't know what pi was. Nobody knew what pi was. So they had to figure out what pi was. And how did they actually get it? How did they actually do it?
They got,
Small triangles and rectangles.
no, they just got larger or more and more sides until it ended up being the angle is closer to.
Okay, yeah, so this method, you may have seen something like this, is what's called the method of exhaustion. And this is the way they did it. So they had this circle, right? And they're like, okay, we really want to know what the area of that is. So they decided they would come in here and draw a triangle, right? And they'd say, okay, that triangle is kind of close. And then they would draw another one, another one, another one. Because they were good at drawing triangles, and they could get areas of triangles, and they're good with that. But see, everything in the yellow is error, right? E-R-R-O-R, error. So what they would do instead is they would come back in here and they'd say, all right, let me see, what can I do? And they said, I'll take a smaller triangle, right? And I'll put smaller triangles in there. And if I zoom in, you can kind of see, whoa. I think you can get the point here. I can't zoom in anymore, but you see we still have error, right? But it's less error. And so what would really work for us here is if there was a way that maybe we could get even more triangles in there. So I've got to make the triangle smaller, don't I? So those are even smaller triangles, which means I'd need more of them, right? And so someone would sit there, and try on a piece of paper with as straight of an edge as they could get, and they would get really, really, really small triangles in there, or sometimes they would use rectangles. It just depends. They would use different things, or polygons, and they would try and figure out a way. And what happened is they were able to get really, really close.
They got exhausted and just put a number.
And then they get exhausted, and then they get to something that they all were comfortable with. And I believe the one that they really liked to use was 22/7. They used that for pi for a long time because it was close enough for what they were doing. So instead of saying the area is pi r squared, what is 22 divided by 7 on your calculator? 3.14, and pi is close to 3.14, right? In fact, most of the time that you do calculations in math classes, they say just use 3.14, right? So this was good enough for a lot, but it wasn't the exact area. They knew that it was pi, or the real area was not going to be found using this. Okay? Understand? But the method of exhaustion of coming up with this smaller and smaller triangles is really where we're headed here. Okay? Because theoretically, how would you find the true area? You would take each triangle, and what would you let happen? You would shrink it down until what? Until it closes up to a single line. And then you take every single line, and wouldn't you get the true area? What's the problem with that? The line has no area, right? The line has no area. So it would be a double problem, because if you let the triangle come to a line, you have no area, and you would have infinitely many of them, wouldn't you? And you can't add up an infinitely many number of things, can you? Or can you? And that's what Newton and calculus was able to figure out, is that there's still a way to do this to get the exact answer, but it's going to require something from Cal 1, the limit. Right? The limit allowed us to go and send a number to a certain place without actually ever getting there, right? And that's exactly what we're going to do here. We're going to let the number of those go to infinity. If we let the number of triangles go to infinity, that's equivalent to saying letting their angle come down to 0, wouldn't it? But it's a limit, so we know we can get answers with limits. All right, so this was, that's just another picture. Now, before I proceed, I wanted to have you remember that there is a formula from pre-cal for the area of a triangle. Everyone just told me area equals 1/2 base times height for a triangle? Yes? So is this one? Someone gives you a triangle. If you know the height and you know the base, you know that the area is 1/2 base times height. But that formula, does anyone here remember seeing that one? 1/2 area is 1/2 AB sine theta. This formula is a little more powerful. I just wanted to remind everyone of it. If you come to a triangle like this, a lot of times you don't know the height of a triangle. A lot of times you know two of the sides. So like this side here, I'll call it A, and this side right here, I'll call it B, which will also be the base. If you know the angle between them, theta, then the area of the triangle changes to that formula. Nobody remembers this from pre-cal? So most people think that this formula is like magic or something, right? But check this out real quick. What is sine of theta? Everyone tell me right now, what's sine of theta? Sine of theta is what? H over A. Solve for H. A sine theta. Agreed? Rewrite this formula. Replace H with A sine theta. And what do you get? That formula, right? So all this is just an application of redrawing your triangle and coming up with the relationship. And all right. So when they were trying to find, the reason I put that up there is because when they were trying to find the area of the circle, and let's say we had a cut here, and I'm trying to find the area of that triangle right there. If I knew the angle and I knew the radius, wouldn't that be the same as having this angle and A and B would be the same number? Yes, A and B are the same number. So R and R basically. And so they could find the area with that formula really easily. I'm just showing you that. I just want you to see that. And that's how they could get the calculation quickly. And how would they know the angle? Well, if they say I'm going to cut it into 4 triangles, what would the angle of each one be? 90, right? So that's 360 divided by 4, that's 90. If they decided to cut it into, let's say, 45, right? This would be 8 triangles. So that would be 45. So they could keep doing that over and over and over and over and over, right? All right. Now, with all that in mind, okay, the idea that if you want to try and find the area of something that is complicated, that you can do this thing where you add things up and add more and more and more and more of them and then try and get an area that way. Let's take a look at this distance problem. Ron, what's going on there, buddy?
I remember all this.
What's that?
I remember everything
You remember everything?
from Riemann Sums. Yeah.
So that gives you the authority and right to just text on your phone and chill out in here? If you know it, you can leave. I mean, I have no problem if you leave and go outside and text or, go home and text, just not in here. Okay? All right, so let's say a person walks at a constant speed of 2 miles per hour. Maybe you shouldn't have sat in the front. Maybe you should have taken that seat in the back. I may not have seen you. I know, right? Ron messed up. Got called out. All right, so let's say a person walks at a constant speed of 2 miles per hour. And what we're going to do is we're going to plot time versus speed. Right? So, constant speed. Go ahead. Hurry up. I don't think I've ever had anyone take me up on that. Wow. I think that's the first time anyone has ever accepted the option to leave. All right, I'll take attendance here in a second. All right, so would you agree that a person walks at a constant speed of 2 miles per hour? That would be the graph of their speed. Look, I'm plotting speed, right? So speed is 2 miles per hour, so at every point in time, their speed is 2 miles per hour. How far have they gone in 3 hours? So let's say this is time 1, 2, 3 hours. They've gone 6 miles? Would everyone agree with that? How does that tie into this picture? It's the area. Look, if you create a rectangle going from 0 to 3 and go straight up to the actual graph, and you look at the area of this rectangle, the area of that rectangle is 6, isn't it? The area of this is 6. Is it coincidentally that it's also how far they walked, or is that the way it will always be? What do you think? Do you think that if you have speed here and you have time here, that the area underneath the curve on that time interval will always represent the distance? What do you think? Or was it coincidence? What do you think?
Always.
It's always going to be that way. All right? It's always going to be that way. Now, why? Well, Just think about if I took just a slice of this. Imagine I just take a slice of this, right? Just take a little slice of it. Would you agree that the width of this slice is a measurement of time? Yes? This is a time measurement. And do you agree that the height of this slice is a measurement of what? Speed? And do you agree that when I do area, I do time times speed? Time times speed. Right? And we have the classic formula from physics that what? Well, there's a couple of them. That relates time, speed, and what is the definition of speed? Speed is distance over time, right? So if I multiply both sides by time, distance is time times speed. So this has got to be a measurement of distance, right? So this little area is the measurement of how far I went on that little sliver of time. Agreed? And if you add them all up, that gives me the total distance I traveled. Okay? Now let's look at another problem similar to this. How far does this person go between the hours 2 and hours 5? So we have a different picture. This time, I'm not telling you what their speed is. You have to look at the graph. I'm sorry, I need to... silence this thing. So we have something like this. It looks like, does that look like one, two? I can't even tell. Between 2 and 5. Are we going to say up here at 2 it's at 1? Is that good enough for you?
Yeah.
Okay. So at 2, I'm up here at 1. And then at 5, where do y'all think I am at 5? Up at 3? Yes? So in this case, I only want the distance traveled between the 2nd and 5th hours. So I want this distance between here and here, right? Which we just said should be the area underneath that curve, which would be everything in here, right? So how would you find that area? How would you do it?
There can be a line where dividing it into a triangle.
Okay, so you want me to actually split it into 2, make a rectangle here, call it R, and then make this one a triangle T, then find the area of the rectangle, then find the area of the triangle, and then add the 2 together? Right? You could do that. What would the area of the rectangle be? So how tall is it? How wide is it? 3. 1 times 3, right? So this would be 3. And then what would the area of this one be? So how tall is it? 2. How wide is it? 3. So 2 times 3 is 6, but then half, right? Because triangle's half. So that's also 3. So what would the total distance be? 6. Was it miles? Was that the same answer as the one before or no? It was, right? Just coincidentally. But the most general idea here is just that it appears that if we can find the area underneath the curve, that can have very, very, like real, what's the word I'm looking for? I guess application, but it can be tied to physical quantities and it can have meaning, right? It can have actual meaning. Rather than just, oh, cool, we found the area underneath the curve.
Relational value.
What's that?
Relational value.
Yeah, relational value. Yes, I like that. All right, so how about this one? I'm going to make this a little bigger so you can see this. This time I actually gave you the function. I said, how far does a person go between hours 0 and 3? So here's the curve. I even tell you that the curve is f of x equals x squared. And at 3 and at 0, we all know that at 3, x squared is 9, right? So we need to find the volume. We need to find the area underneath this curve, don't we? What's the problem, though? It's curved, right? This is curved. This is not a triangle. We can't create a triangle, right? So how are we going to do this? With an integral somehow, yeah, but we don't know that yet. We're acting like we don't know that, right? Somehow this has got to be done, right? So we're stuck. So Riemann was a mathematician who was first to come up with an actual attack for something like this, and he called it Riemann Sums, or we call it Riemann Sums today. And it was just a way of generally trying to attack a function by approximating it with a bunch of rectangles. So take a look at this picture here. We need an efficient way of determining the area under functions. We use areas of rectangles. And I think I have a better animation here. Yep, there it is. So I did show you this, right? Okay. So what I want you to see right now is the blue curve is x squared, right? That's x squared, even though it doesn't really look like it.
Bless you.
And what I'm doing is I'm approximating x squared with one rectangle. So I'm going to sit here and I'm going to measure the width right here, and then the height the whole way up, and measure that. And that area is going to be what? How wide is this? This is 4 wide, right? 5 minus 1, that's 4 units wide. How tall is it? 5 squared is 25. So it's 4 wide, 25 tall. So the area of this entire rectangle would be 100. That's way over what it should be, right? The true area under that blue curve, that's an overestimate. So what I can do instead of using one rectangle, whoa, what the heck? Is I can use 2 rectangles. And this time, instead of going all the way across, I'm going to go halfway, right? Halfway, I'll go straight up, over, and then find the area of that rectangle. On this one, straight up, over, find the area of that rectangle. Add those 2 up, and that'll be an approximation, right? And the computer's actually doing it for us right here. We get 68. Can y'all see 68 right there? But again, that's too much. The true area is 41.333. And we'll talk about how we get that in a minute. I could do 3 rectangles, 4 rectangles, 5 rectangles, 6, 7, 8. And look what happens. The area is getting closer and closer to the true area, right? My error is getting smaller and smaller and smaller with each rectangle. Yes? Now, I could really make this draw out quite a bit. We only have 20 minutes left. And we could actually practice doing Riemann sums by hand. And they become very, very tedious. There's a lot of messy stuff inside of Riemann sums. And you learn how to do these, and then you come up with exact answers. But, and this is the formula for it, actually. It's this limit right here. All right, it looks pretty nasty, but it's doable. But do you see something over here? Do you see this? The integral. The integral. And that's what I want to get to. I'm going to skip over us doing Riemann sums by hands. It's going to be too much work. And time-wise, I'd rather us have more time for Chapter 8. So, but do you understand physically, geometrically, the problem? Yes, trying to find areas? So what Riemann sums says is that if you have some arbitrary curve, all right, and if you are able to take an arbitrary rectangle in here like this, okay, this is the function f, then what I need to be able to do to find the true area is I need to add up, right? I need to add up a bunch of rectangles. And for mathematical purposes, we like to use summations to add up. I'd like to add up the areas. How wide is the area of this triangle? Well, would you agree that, this rectangle, would you agree that each rectangle would have the same width? If I do an equal number of them, the same width? I'm going to call that delta x. Delta x means what? Change in x, right? The distance traveled, a change in x. So this change in x is going to be the same for every single rectangle, won't it? Yes? The height of the rectangle is never the same, is it? It changes throughout as you move from left to right, doesn't it? So the height of the rectangle will always be the function's value at that point, right? So I need to add up the areas. We just said that the area is the height of the rectangle, that's the height, times the width of the rectangle, which we said is what? Delta x. Understand what this formula means? Height of rectangle, width of rectangle. To get together, that's the area. I need to add them up. Then I need there to be an infinite number of them, right? I need to let the number of these go to infinity. So I need to somehow let the number of rectangles go to infinity. And what it was, the big fundamental theorem of calculus, that's what it's called, the fundamental theorem of calculus, says that guess what? If you actually want to know what this limit is, you need to be able to find the antiderivative of the function. And I'm not going to prove the fundamental theorem of calculus in here. But this turns into this. Now let's see if we can see why it is that this becomes this. Do you see now that the f of x is actually just the height of the rectangle? Do you see that the dx is what happens when the width of the rectangles become infinitesimally small? Okay, but it's still the width of a rectangle. The integral sign takes the place of the limit because we let the number of them go to infinity. And so I'm trying to get you, I guess, to see that every time you look at an integral, these pieces are usually connected to some geometric picture. And that's going to help you later, because we're going to be rotating these things around the axis and spinning them around, and then you're going to be creating volumes, and you're going to be looking at disks and cylinders, and you're going to be like, okay, well, how does that change this formula? Well, if you know the formula for a cylinder, then it just changes the formula in here. So we need to understand that these two are no longer just arbitrary function dx. It's actually width and height of a rectangle. I hope you're following this. So where do the numbers come in? Where do these numbers a and b come into the play? Well, a and b are the points where you want to start and you want to stop. So if you want to start at x equals a and end at x equals b, then we put a and b here, starting and stopping point. Now, I have 15 minutes. Y'all look like everyone looks demoralized. Should I not have kicked Ron out? Or have you? I didn't kick him out. He left, right? He chose to leave. Everyone's like, man, I should break out my phone so I can get out of here. All right, let's get back to this question. Find the area under f of x equals x squared on, what was it, 0 to 3, was it? Yeah. Yeah, it was 0, 3. On 0, 3. So we're going to be using some new notation here. We're going to be using what's called the fundamental theorem of calculus, which is also referred to, this version of it is called the evaluation theorem. And it says that if you want to know the area under this function, then of course you're going to come in, you're going to add up an infinite number of rectangles, aren't you? Each of those rectangles is going to be how tall? The function, x squared, times the width of each rectangle, which is going to be the same for every rectangle. It's going to be that little infinitesimally small thing, which we always call dx. This is called the differential. We have always known it as the thing that keeps track of our variable, right? But now this has geometric meaning. Then we use 0 and 3 to tell us where to start and where to stop, right? According to the evaluation theorem, the answer to this, all right, will be equal to, and I'm going to write the evaluation theorem up here. What was capital F? If this was little f, what was capital F? The antiderivative, right? That's the antiderivative. So what this says, the evaluation theorem says, what I need to do is just write down, right here, write down the antiderivative of x squared, of this right here. What's the antiderivative of x squared? 1/3 x cubed. Okay? Then draw this little line next to it, and then put the a on the bottom, which was 0, and then put the b on the top, which was 3. Now, all this is, in the evaluation theorem, is just a place for you to write the antiderivative down. That's all it is. This is just a place for you to write it down, and then for you to put the numbers here to keep track of your two endpoints where you're starting and stopping, right? That's what that is. Then the next part equals this right here, means you take capital F, which is this, right? And you plug what into it? B, which for us is what? 3. So what I'm going to do now is I'm going to set up a set of parentheses. That's for this one. Then I'm going to subtract from that this one, capital F of A. So I plug 3 into here. I get 1/3 times 3 cubed minus, the next one will be 1/3 times what? 0 cubed. And this goes away. And what's 3 cubed? 27 divided by 3? 9. And that's it, right? That's it. And the fundamental theorem of calculus and the evaluation theorem says if you want to find the area underneath the curve between 2 points, all you have to do is be able to find the antiderivative. If you can find the it's a perfect segue. Find the antiderivative. All you need to do is find the antiderivative, right? Once you do that, you plug in your 2 endpoints. Be careful though, because it's always the b first, then subtract the a. It's not the other way around. Right? That number, miraculously, is the area under the curve. Yes?
Is the f of b minus f of a just supposed to be the delta x in the fundamental theorem?
Is it supposed to be the delta x?
Yeah, like or the limit n to infinity summation f of x.
All that stuff? Is it? I'm not quite following you. Like this? Oh no, in this formula, is it this part? Is that what you're saying?
Well, because what we wrote earlier on that curve you drew, the limit n to infinity and then summation f of x times delta x.
Yes.
Is that supposed to be the delta x part there? Or I don't know.
No, all that is, this right here is the notation that we use to represent that whole entire limit. Okay? This integral sign is the thing that's saying limit going to, because if it was just add up, why not just use a sum? The integral sign is special in the sense that it's a sum, but it's a sum of an infinite number of pieces that are getting, right? Each of those rectangles is getting more narrow, more narrow, more narrow. So it's just a special symbol for that crazy looking limit.
Thank you.
All right, you're welcome. So this opens up the possibility of, anything you can integrate, you can find areas under, right? Anything you can integrate. I like this one. Let's do this one. Find the area under cosine x between 0 and 2 pi. Find area under f of x equals cosine x on the interval 0, 2 pi.
Did you break it up?
We could, yes. We'll talk about that in a second. Let's just try and apply the fundamental theorem real quick. Also, let me just say, the Riemann Sums thing, it's, I've spared you quite the torture with Riemann Sums, okay? Riemann Sums is it's kind of a nightmare when it comes to just algebra, putting things together. It's tedious, but if anyone wants to see how to do it by hand, please just talk to me. Be happy to share it with you. Some people like that sort of thing. All right, find the area under the curve. So that means I need an integral, right? I need to set up an integral, and the height of each of the rectangles should be cosine x, the function, dx. So dx is still always going to be there because the width's always going to be dx. What are the numbers I put here? 0 and 2 pi. And then equals. So I just need to be able to find the antiderivative. Antiderivative of cosine x is just sine x, and then 0, and then 2 pi, right? That's the notation we use. Just write down the antiderivative, write down the two endpoints. And then I'm going to plug in and get an answer. Which do I plug in first? 2 pi. So sine of 2 pi, and then sine of 0 here. What is sine of 2 pi? 0. And sine of 0 is 0. So you get 0. But I know cosine has area, right? It has area under it. It does, doesn't it? I mean, let me graph it. That's what cosine looks like, doesn't it? So how is this, why is this telling me 0? It cancels out. It actually, it's counting this area right here as positive area. And somehow it's counting this other stuff as negative area. And then this is positive area. And because of the symmetry of the graph, the red part below is equal to the black part above, and then it's going to cancel out and get 0, right? Now, why is it counting it as negative? Imagine a rectangle. If I drew a rectangle right here, the width would be dx, right? What would the height be? Didn't we say it was the value of the function? And isn't the function negative down there? So it's going to count that rectangle as negative. Even though we know areas can't be negative, it doesn't know that, right? It doesn't know that the function can't be negative. So this could be dangerous, couldn't it? So that means we're still going to have some understanding of what the graph looks like to find an area, because if it dips below the x-axis, we're going to need to somehow account for that somehow, right? So what would be a better way of doing this problem if we wanted to find the true area under this? How could we do it? How do you think we could do this? Split it up, right? Like first go from 0 to whatever this is, then go from here to here, and then from here to here. So what are those numbers? Where are those occurring? Pi over 2 and 3 pi over 2. That would only give you this top piece, right? I'm not sure. You're saying go from here?
Yeah. Is that what you call like a gap? Like have a part.
You're saying just find out what this is from here to here? I'm not following you. That's
And I guess erase the end part, the third part? Yeah, attach that.
oh, okay. You mean move that over here? Yes, you could use the symmetry of this graph against itself. In fact, you could just find one of these, right, and then multiply times 4, because there's 1. Cut this in half. 2, 3, 4 of them. That would be your answer. But not all graphs are going to be nice and symmetric like this. So the standard protocol would be to break it up in different pieces. So instead of doing this integral that we just had, if we want to find the true area, our integrals would look more like this. We would do first an integral that goes from 0 to pi over 2 of cosine x, right? That would take care of this piece. Then what about this piece? We know that if we go from pi over 2 to 3 pi over 2, we know that that answer is going to come out to be negative, right? So instead of adding it, we're going to do what? Subtract it, because I know this answer is going to be negative. And so when I subtract a negative, it's going to become plus. And this one would go from pi over 2 to 3 pi over 2. I'm sorry? How do you graph cosine? My graph may not be that great. Where's cosine 0? Right? That's what this is saying? Where's cosine 0? Where's cosine 0? 90 degrees and 270. Pi over 2 and 3 pi over 2. You following? Right, this is the cosine curve, right? I want to know where it hits the x-axis. It's at those 2 points.
So
Yes.
with a graph that's kind of not as nice, would we just use those points as our zeros?
You would have to find the x-intercepts of the graph. Yeah.
Yeah.
Yep. So you'd have to set the function equal to 0 to start, figure out where those are, and then you'd have to break up your integrals. I'm going to have a total of 3 integrals here. But I want to make sure everyone's okay with where I'm getting these numbers from. Okay. And the last one, what should I say here? Plus or minus? Plus, integral where to where? 3 pi over 2 to 2 pi of cosine x. I'll let you finish this one out yourself. But look, all 3 of these have the same antiderivatives, don't they? Antiderivative of all of those is sine. The only difference between these 3 integrals is that at this one you're going to evaluate it at these 2 endpoints. And then on this one you're going to evaluate at these 2 endpoints. Here, these 2 endpoints. And when you put this all together, you should get a positive number. I believe it's 2, but I could be wrong. Let's see if I don't think I did it here. No, I didn't.
Is
Okay.
there a negative sign over here because it's under the curve?
Where, here?
No, there.
Here, yes, this is, see, we already know that this integral right here is going to spit out a negative number. And we know that because it's measuring, this right here is the height of the function. And we know that in this little interval, the height of the function is negative. So it's going to be a negative number times dx, which is a positive number. We're going to be adding up a bunch of negative numbers. It's going to be negative. So we subtract it to turn it back into a positive. We're going to have more time with this. In fact, I'm not giving you any homework over this. All I'm doing is telling you to finish off the partial fractions. And then in addition to the partial fractions, everybody likes bonus, right? Everybody loves bonus. So